Hello and welcome to the second lecture on multi-degree of freedom systems. In the earlier lecture, we talked about the development of equations of motion. On the examples for the development of equations of motion, we talked about the multi-degree of freedom equations for n number of degrees of freedom, and we also talked about solving the differential equations of motion. In this lecture, we would be talking about static condensation. Next, we would be talking about certain examples on static condensation. So let us begin. We know that we have already studied discretization in the earlier lecture. And what did we get to know from discretization? That we could take out or eliminate certain degrees of freedom if, for example, we have certain assumptions. For example, we had one of the assumptions was that the axial deformations of the columns are negligible and the beams are strictly rigid. Thereby, we could eliminate many degrees of freedom, both translational, vertical, as well as the horizontal translations were to be concentrated at certain particular place. Now, in static condensation, what is done is that we are basically eliminating from the dynamic analysis those degrees of freedom of a structure to which there is no mass attached. So, there are all the degrees of freedom are thereby included in the static analysis, but we are actually condensing the matrix into the knowns and the unknowns. Now, how is it done? Let's take an example of a two-bay, two-story frame shown in the figure here. When with axial deformations in structural elements being neglected as was neglected in discretization methods, the system now has 8 degrees of freedom for formulating its stiffness matrix. Now, these are 1, 2, 3, 4, 5, 6, 7, 8 from U1 to U8. Thereby, as discussed earlier in earlier section, in earlier topics, we come to know that the mass of the structure is always idealized either at the floor level. Now here the mass can be idealized at nodes as point lumps, and the mass matrix now contains 0 diagonal elements for rotational degrees of freedom, but certain known values of mass for translational degrees of freedom. Now, these are the degrees of freedom that we can eliminate from the dynamic analysis of the structure, provided that the dynamic excitation does not include any external force in the rotational degrees of freedom. Now, even if we have included or formulated the stiffness matrix, the vertical degrees of freedom can be eliminated from the dynamic analysis, because the inertial effects associated with any vertical degrees of freedom are usually small, provided that the dynamic excitation does not include vertical forces at the nodes, as in the case of horizontal ground motion. So let us recall from the earlier lecture, wherein we studied about the development of equations of motion. You can see that the elastic mass component is dependent on the stiffness, and this is the stiffness matrix. So this is the elastic resisting force matrix number 1, where Fs is Ku, K is the stiffness matrix. Second is the damping matrix, where C is the damping matrix, and third is the mass matrix from the inertial resisting forces. Thereby, now having this knowledge, we could write down the equation of motion. Now, what was the equation of motion? Mu plus Ku plus Cu is equal to Pt. Now, in terms of matrices form, in terms of matrices, it could be written as M 1 up till mn, m11 up till mnn, so on, into u1 into un double. If you write this down into, now we can easily divide this matrix into two components, the non-zero ones and the zero ones. There are certain degrees of freedom like u0 which are associated with the 0 degrees of freedom, and ut which have certain value at any time t. Now thereby mtt is the mass matrix here for the translational degrees of freedom, and u0 is the degrees of deformation associated with the rotational degrees of freedom. Similarly, ktt will be the stiffness component associated with the translational degrees of freedom, and kt0 and k0t, these are the degrees of these are the stiffnesses associated with the known ut, u0 and ut. Thereby we have condensed the matrix into between 0 elements and certain other elements. Now there is no force associated with the rotational degrees of freedom, then this becomes applicable. Now u0 thereby defines the degree of freedom with zero mass, and ut the degree of freedom with certain mass. Now these are the known dynamic degrees of freedom. Thereby kt0 here is equal to k0t transpose. They are transpose of each other. So now we have divided the matrix into 4 individual matrices. So the two equations that we get from here are, number 1, mtt ut double dot plus ktt ut plus kt0 u0 is equal to pt. So this is an equation of motion associated with the known force pt. Second is k0t ut plus k00 u0 equal to 0. This is the equation of motion associated with no force acting on the system. Now from the second equation we can obtain u naught is equal to minus k double naught raised to power minus 1 k0t ut, and if now we substitute this in the first equation that we obtained, what we get is mtt ut double dot plus ktt hat ut equal to ptt. Now here ktt hat is the condensed equation of stiffness, so it's the condensed stiffness matrix, and we can say that ktt is equal to ktt minus k0t transpose k00 raised to power minus 1 k0t. Thereby what we have obtained from here is a condensed stiffness matrix. Now this condensed stiffness matrix is what will be applicable in solving the equations. Now where do we use this? Once we have to determine the solutions for, we provide the displacements ut in the dynamic degrees of freedom, and at each instant of time the displacement u0t in the condensed degrees of freedom are determined. So this is the way in which we determine the unknown degrees of freedom. Now here we are starting with an example. This is an example of a cantilever, a massless cantilever beam of length L. It's supported on two lumped masses. It supports two lumped masses. One is ml by 2 and another one is ml by 4 at midpoint and at free end as shown in the figure. The flexural rigidity of the uniform beam is EI, with the 4 degrees of freedom chosen in this figure, and the applied forces P1 and P2. What we are going to first determine is the equation of motion, and next then we are going to apply the static condensation to solve same in equation of motion for determination of UTs. Now here in this let us first start with that this beam has 2 beam elements and 3 nodes. Now the left node is constrained and the other 2 nodes have 2 degrees of freedom. Now which are the 2 degrees of freedom? Number 1, you have P associated with P1, and number 2 you have associated with P2. With P1, U1 and U3 are associated, translational and rotational, and with P2, U2 and U4 are associated. Now thereby this gets divided into 2 elements, element 1 and element 2. Thereby the displacement vector here would be U equal to U1, U2, U3, U4, a matrix composed of these. Thereby now let us move to solving this question. What we are going to do is that first we will determine the mass matrix. Now what is the mass matrix for this set of equations? The mass matrix would be M1 and M2 associated with U1 and U2. And what is M1? M1 is ml by 4, and what is M2? It's ml by 2. Thereby we could first get a mass matrix. Next is the determination of the stiffness matrix. Now how is that done? Now there are various methods which we can use to determine the stiffness matrix, but here if we look at the equilibrium matrix or the direct equilibrium method of determining the stiffness influence coefficients, what we get is first from the first figure. If we have to determine the first column of the stiffness matrix, what we do is that we first impose U1 equal to 1 and all other U2, U3 and U4 will be equal to 0. The stiffness influence coefficients here are KIA1. The forces that will be necessary at each node of each beam element to maintain the deflected shape are determined from the beam stiffness coefficients. Now here it's given in this figure. Now these are 24 EI by L square, and another that's a rotational force that is required to have a unit displacement. The translation is 96 EI by L cube, and this is so K. If we have a look at this, what will be K11? It's 96 EI by L cube. Then what is K21 is minus 96 EI by L cube. K31 is minus 24 EI by L square, and K41 is minus 24 EI by L square. Now where did we get this from? This is from many methods you could use in order to determine this. The slope deflection methods that you must have studied earlier, wherein you give a unit a displacement and then obtain the other rotations and the deformations associated with it, the thetas and the deltas. Next is, once we have determined this, what we do is we have to determine the second column of the stiffness matrix. What for that what we do is that we put u2 equal to 1 and all u1, u3 and u4 equal to 0. The stiffness influence coefficients now here are ki2, and these are the forces on each beam element which are necessary to maintain the imposed displacements. The two sets of forces that we are obtaining are shown here in these figures, and we can see that K12 here is minus 96 EI by L cube for a unit rotation. These are the values, and K32 is 24 EI by L square. Sorry, this is unit translation itself. K22 is 96 EI by L cube plus K96 EI by L cube, that's 192 EI by L cube, and K42 is minus 24 EI by L square plus 24 EI by L square, and it's overall equal to 0. So the third column of the stiffness matrix is obtained. Similarly, once we put u3 equal to 1 and all other u1, u2, u4 equal to 0, and thus we obtain K13 equal to minus 24 EI by L square, K23 equal to 24 EI by L square, K33 equal to 8 EI by L, and K43 equal to 4 EI by L. This is shown again in the figures here. Next we obtain the fourth column of the stiffness matrix by imposing u4 equal to 1 and all other u1, u2, u3 equal to 0. Thus we obtain, as shown in the figure now here, K14 will be minus 24 EI by L square, K34 will be 4 EI by L, K24 will be minus 24 EI by L square plus 24 EI by L square, and K44 will be 8 EI by L plus 8 EI by L, that's 16 EI by L. Now all the stiffness influence coefficients once determined, we have the stiffness matrix now that we can write down. Thereby now we can write down first the mass matrix, and we have already discussed this. M1 will be ml by 4, M2 will be ml by 2, M3 and M4 there is no mass associated with the rotational degrees of freedom, so they will be 0. Next we are going to determine the stiffness matrix. This is we already have determined the values of K11, K12, K13, K14, similarly K21, K22 and so on. Now these values are substituted here, and a stiffness matrix is determined in terms of ATI by L cube. Now this matrix, apart from this matrix, what is known to us is the load matrix, which is P1, P2. There is no load associated with P3 and P4 because they are the rotational degrees of freedom. No load is considered to be attached to them. Next, what we do is that we have to now determine the response to the next we have to determine the response and the static condensation response. In static condensation, what is known to us is that ut is u1, u2 here, and u0 is u3, u4. These are the zero the rotations are taken here as 0 ones. Then mtt is known to us is ml by 4, ml by 2, whereas m00 will be 0, 0 here if we take from the static condensation principle. You just go back some slides where we discussed about mtt and m00. Now what is pt? It's p1 and p2, and what will be p0? It will be 0, 0. Now what is the stiffness matrix K here? What is that equal to? As we have already determined this earlier, it's KTT, KT0, K0T, K00. Now KTT is the matrix of those known elements of 12 minus 12 minus 12 24. These are the known elements, and kt0 is minus 3l 3l minus 3l 0. These are those which are associated with the rotational and degrees of freedom. So we actually tear the matrix apart into four components, into four matrices. Thereafter we obtain ktt, and that is 12 minus 12 minus 12 24. From there, now we can obtain ktt hat. I have already given you the formula for ktt hat, which is equal to the which is determined, which has been determined earlier, and we can determine this matrix, which is equal to 48 ei by 7l cube, 2 minus 5 minus 5 16. Finally, we can then determine u naught, which is equal to t uf. Now t is given to you as 1 by l 2.57. this is what is determined. So thereby we have determined the condensed stiffness matrix, and we can use this in the equation of motion in order to determine the forces associated with it, that is ut forces associated with them.